Let's study effectively with Miss ICT Skill Builder.
Imagine you have 10 playing cards face down on a table, and you need to find the ace of spades. You don't know where it is, and there is no pattern to how they are arranged. This is one of the most common problems in programming, locating a specific piece of information inside a completely unsorted dataset. The simplest way to solve this is a linear search. You check the first card. If it isn't the ace, you check the next one. You repeat this process, moving one by one in a straight line, until you either find your target or run out of cards. A computer does exactly the same thing using an array. It stores the data sequentially and tracks the position using an index. Because computers start counting at 0, the very first item is at index 0, the second is at index 1, and so on. The search algorithm simply loops through these index numbers one at a time. Looking at example 1 from the text, we can see this step-by-step process. If the computer is searching for the number 4, it compares 4 against the first index, which holds a 5. It's not a match, so it moves to index 1, which holds a 3. It keeps checking until it reaches the 4th number, identifies the match, and stops. Checking 4 numbers takes a fraction of a millisecond, but programs scale rapidly. If a database has millions of unsorted user profiles, running a linear search means the processor might have to check millions of records just to verify a single username. That takes a massive toll on computing time and system memory. To avoid processing delays, developers need a way to organize their data. By arranging the information into a specific order first, they open the door to much faster lookup methods later. This brings us to a standard organizing method called the bubble sort. Its entire job is to take a chaotic dataset and rearrange it into a predictable sequence, like ascending numerical order or alphabetical order. The algorithm operates on one strict rule. It only looks at 2 adjacent items at a time. It compares the left value to the right value. If the left value is larger, they swap places. If it isn't, they stay put. Then the algorithm shifts one position to the right and compares the next pair. This data table shows the first pass of a bubble sort on 4 unsorted numbers. The algorithm starts by comparing the 6 and the 2. Because 6 is larger, it swaps them, placing the 6 in the second position. As the algorithm moves that in the line, that 6 is now compared to the 5. It's larger, so they swap. Finally, it compares the 6 to the 1. It swaps with the 1, pushing the 6 into the final slot at the far right. Notice what happened. Completing that entire sequence across the row locked exactly one single piece of data into its correct sorted position. The rest of the numbers left behind might still be completely out of order. Because one full pass only places one number accurately, a standard bubble sort is forced to repeat the entire looping process over and over. To guarantee every item is sorted, it has to run through the list a total number of times equal to the number of items minus 1. We see this rigid structure in the version 1 pseudocode. The loop is hard-coded to run for the full length of the array minus 1. That means if you have 100 items, the code will execute 99 full passes, no matter what. But consider a list of 4 numbers that happens to look like this: 1, 2, 5, 6. If you run a complete bubble sort pass on that specific list, how many times will the number swap? 0. As the algorithm evaluates the pairs, the left number is never larger than the right. If the program completes a full pass without making a single swap, you have mathematical proof that every item is already in perfect order. To capitalize on this, developers introduce a Boolean variable to the code, a simple true or false flag. At the start of every pass, they set a variable called changes to false. If a swap happens, they flip that variable to true. This creates a new stopping criteria, outlined here in the text. At the end of a pass, the program checks the flag. If changes is still false, it knows the list is sorted and immediately halts the algorithm. Adding this one condition breaks the rigid loop. A list of 1,000 items that happens to be sorted after 3 passes will now stop at 3, instead of pointlessly executing 996 more times. Deciding which of these algorithms to use comes down to balancing the immediate speed of searching against the upfront processing cost of sorting. If you're handed a messy dataset and only need to look up a value exactly once, running a bubble sort is a waste of processing power. It is much faster to simply leave the data unsorted, run a linear search, find your target, and move on. However, if you are building a system where users will search that same dataset hundreds or thousands of times a day, the math flips. Investing the heavy processing power up front to bubble sort the data allows the system to utilize highly optimized search techniques down the road, saving time on every future query. To recap, a linear search steps sequentially through an array index by index until it finds a match. A bubble sort loops through an array, swapping adjacent pairs to push the largest values to the end, stopping either after n-1 passes or as soon as a full pass occurs with no changes. Writing code is only part of the job. True problem solving requires evaluating your dataset, predicting how it will be used, and deploying the exact algorithm that matches those constraints.
Thanks for watching. If this helped you clear up the concept, hit that like button and share it with a friend who might be struggling with it too. Let's build those skills together.